Welcome to EDU World Space.
In this problem on gravitation, we are told that a hammer with mass m falls from a height h above the Earth, and this height h is not small in comparison to the radius of the Earth, re. We are asked to derive an expression for the final speed of the hammer just before it reaches the Earth's surface. We'll write our answer in terms of h, re, and me, where me is the mass of the Earth. So we'll apply the conservation of energy in this problem, and we'll call position 1 the initial position of the hammer when the hammer is at rest, and position 2 is the position of the hammer at the Earth's surface. The distance between these two positions is obviously h. So we'll call the distance r1 to be the radius of the Earth plus the distance h. So essentially that's the distance from the initial point of the hammer to the center of the Earth. And the distance r2 is the point where the hammer is at the surface of the Earth. So that distance is re from the center of the Earth. Now, applying conservation of energy, we know that the initial kinetic energy plus the initial gravitational potential energy plus any external work, we'll call it W other, must equal the final kinetic energy plus the final gravitational potential energy on the hammer, K2 plus U2. Now we know that only gravity does work, so this term becomes 0. Now let's write down each of the other terms. So the kinetic energy initially is equal to 0 since the hammer is at rest. The final kinetic energy, K2, is equal to a half m, where m is the mass of the hammer, V2 squared. The initial potential energy due to gravity, U1, is equal to minus g m, the mass of the hammer, times me, the mass of the Earth, divided by r1, which we can write as minus g m times me over h plus re. So that's the gravitational potential energy at the hammer's initial position. At the final position, the gravitational potential energy relative to the center of the Earth is minus g times m times me divided by r2. And r2, remember, can be written as follows. So this is minus g m times me over simply the radius of the Earth. So now the hammer is at the Earth's surface. So therefore, if we go back to our conservation of energy equation, we have that minus g times m times me divided by h plus re is equal to a half m V2 squared, the final kinetic energy of the hammer, minus g m me divided by re. So what we can do is we can rearrange this equation and we can solve for V2, since V2 is what we're looking for. So V2 squared is equal to 2g times the mass of the Earth, me, into 1 over re minus 1 over re plus h. And this can be written as 2g times the mass of the Earth, me, divided by re into re plus h. So we're doing some mathematics, and this is multiplied by re plus h minus re. So we can see the re's cancel, and we are left with 2g me times h divided by the square root of the radius of the earth re into re plus the height that the hammer falls, h. So therefore, the velocity of the hammer v2 is equal to the square root of 2g me times h divided by re into re plus h. So this is our final answer. This is the final velocity for an object that falls any distance that is not small in comparison to the radius of the earth.